We are still talking about estimation of the design flow. I just would like to remind you that we still need to talk about the estimation of the flood hydrograph. So we are still speaking about peak flow, and I think it is useful that I make this remark because we shift on the other hand to rainfall runoff modeling. And rainfall runoff modeling, as I mentioned to you yesterday, in principle allows you to simulate the whole hydrograph. And yesterday I said I am now introducing rainfall runoff modeling, but for now I'm still dealing with the estimation of the peak flow. And therefore I introduced the rational formula, which, as I told you, it's a rainfall runoff model, because it is a rainfall runoff model, even if it looks like an empirical formula. It's a rainfall runoff model that allows us to estimate just the peak flow. In principle, it's not used in almost all applications. It's never used for estimating the hydrograph, even if in principle it would be possible. But usually the rational formula, it is used for estimating the peak flow. So let's focus on it for the peak flow estimation. And as I said, it's CIA. So basically there is the product of runoff coefficient C, rainfall intensity I, and the catchment area A. And I mentioned to you yesterday, and then I stopped my yesterday's lecture, that there are key issues here in estimating C and I. I is rainfall intensity. First, let's see that the formula is dimensionally homogeneous, because as I said, the rainfall intensity is measured as a length over time. It's a rainfall depth over time. So basically, if you write the formula, the rational formula as CIA in dimensions, it looks like the cube of a length over time, because the river discharge is a volume per unit time, so it's the cube of a length over time. This is adimensional, see. I is a length over time, and the area, of course, is a square length. So it's dimensionally homogeneous. And but it is dimensionally homogeneous, but you have to be careful on the units, because usually the river discharge is measured in cubic meters per second. Rainfall intensity is usually measured in millimeters per second, and the catchment area is usually measured in square kilometers. So you have to be very careful when you when you plug in the individual factors in the formula. You have to be careful about the units, because this is a typical mistake that we make. And that being said, let me talk about of the rainfall intensity, because estimation of the rainfall intensity is a key task. Here I mentioned to you that rainfall, when we talk about rainfall, measuring rainfall, we always have to refer to a duration of the rainfall event. So basically we have two issues. First, to define the duration of the event. What is the duration that induces for a given catchment the highest flood? Because there must be a duration of rainfall which is, we call it critical. And keep in mind that rainfall is a phenomenon such that if you increase, as I said yesterday, the observation time span, then you get decreasing intensities. And this is quite intuitive if you think that usually the very violent rainfalls last for a very short time. So during summer, typically, when you get thunderstorms, you get a very high rainfall intensity. You may get it, but typically it is very short. And it's also very limited in space. I'm sure that you experience it sometime while you are driving during summer, during thunderstorms, that in the range of 200 meters you can pass from the sun to a very heavy storm, because this is typical of short and very heavy rainfalls. They are short, but they are also limited in space. So rainfall intensity, if you refer to a short time step, you may experience very heavy intensity. If you increase the time step, like if you look at daily rainfall, of course the intensity is decreasing. The total amount of rainfall depth during a day may be higher, of course, than the rainfall depth over 1 minute. But when you divide by the time, which is 1 day instead of 1 minute, you get a lower intensity. So typically rainfall, I say again, when you increase the time step of observation, you get lower intensities. So basically here, in this formula, if you increase the duration of the event, you get a lower intensity. So basically when you plug in the intensity there, you get a lower value and then a lower value of the peak. On the other hand, you must keep in mind that short rainfall is typically acting for a limited time, not typically, is by definition acting on a limited time. And therefore, if the base in the catchment is very large, basically this rainfall has an effect on the river flow that is not significant. Let me make an example. If you get the Po River is extended for, as I said, 70,000 square kilometers. If you get a rainfall of 1 minute over this area, typically it is not effective. Why is that? Because the Po River takes, in bringing the water from the Alps to the sea, takes 3 days. And therefore you understand that if you get a 1 minute rainfall, even if it is extended over the whole basin, not to say that usually it's not, because very heavy rainfall usually and short time rainfall are, as I said, confined in space. But even if it was extended over the whole basin, you understand that 1 minute rainfall for the upper part of the catchment gets to the closure after 3 days. So basically there is a smoothing effect of the catchment. Because, of course, there are some areas that get to the sea soon. So if it rains close to the sea, then the effect on the river flow is got at the closure of the catchment soon. But the effect of the upper part of the catchment, you see it after 3 days. So it's intuitive that a 1 minute rainfall in a so large catchment is not very effective, very significant. On the other hand, in a very small catchment, which takes 1 minute, for instance, to get from the utmost, from the farthest point to the closure, a 1 minute rainfall is indeed significant, because you understand that if it gets 1 minute to get from the farthest point to the closure, a 1 minute rainfall, then it's causing a significant effect. And therefore, this reasoning brings me to say that depending on the size of the catchment, it's not a good idea here to plug in a very short rainfall, because you would get a value that is very high, but on the other hand, it wouldn't be physically reasonable. You would get an estimate of the river flow that is very high, because you plug in a very high rainfall intensity. But it's not credible that this rainfall intensity contributes over the whole area to the river flow at the same time. So it wouldn't be reasonable to plug in a very short rainfall intensity. And let me make, in order to make this concept clearer, let me make a sketch. So let's get a catchment, and let's suppose with a river, and let's suppose that the concentration time, Tc, is 3 days, like the Po River. Okay? So let's suppose that you get this rainfall which lasts 1 minute over the whole area. Okay? What happens? It happens that the area that is close to the closure of the catchment, you get the corresponding river flow very soon. But while this area is contributing to the river flow, this area up there is not contributing. because it takes 3 days for getting from here to the closure. So it rains, and you see very soon the contribution of this area, but not of this one, because it takes time. Now, let's suppose that time passes. After some time, this area has already contributed, so it doesn't contribute anymore. What is the area that contributes then to the river flow? It's the area, maybe this one. So after some time, you get this contribution, but you don't have anymore this contribution. And you still don't have the contribution from the very far points. And then after another time, you get maybe this contribution. But still, you have small areas contributing at each time. You never have the superimposition of the contribution from the whole catchment. Okay, perfect. Now let me make another sketch. And let's suppose that TC is 1 minute. TC is 1 minute. It rains for 1 minute. What happens? It happens that the whole contributing area is contributing to the river flow at the same time. Because if it takes 1 minute from here to here, and it rains for 1 minute, you get in this minute the contribution from the whole catchment. So, in this case, if I plug it in the rational formula, a rainfall intensity of 1 minute, I would get an estimate of the river flow, which would be very high, because the rainfall intensity is very high, but it wouldn't be reasonable, because I don't have the contribution from the whole catchment. So in order to take this into account, I should reduce A. Because you see that the contributing area is never A. It's pieces of A at each time. Is this clear? So basically, the question is, what is the duration that is critical? And I understand that there is a critical duration. Because if the duration is too short, it's not critical. It's not critical because the contributing area is split in many pieces. If the duration is too long, like I put the duration of 1 year, it's not critical because the intensity is very low. So there must be a time in between 0 and infinite, which is the time of rainfall, the rainfall time that is inducing the peak flow over the catchment. So my question is, what is the duration of rainfall which induces the flood in my catchment? Now, it can be proved under certain assumptions, and I'm not demonstrating this. It can be proved that the critical duration of rainfall is the time of concentration. And you can also understand this by intuition, because what happens, let's remember the definition of the time of concentration. The time of concentration is the time taken by a drop of water from the farthest point, from the point that is located much far from the closure to reach the closure. Okay, this is the time of concentration. It means that if you get a drop which is located in the farthest point from the closure, and you compute the time taken by this drop of water to get there, this is the time of concentration. It means that if it starts raining and it continues to rain, after the time of concentration you have the whole area of the catchment contributing to the river flow at the closure. So it's an intuition that the time of concentration is a critical time. It's intuitive. Why is that? Because it's the time where you get the contribution from the whole catchment. And you can understand that moving beyond that time, it's not a good idea. Why is that? Because the rainfall intensity would decrease. and the contributing area wouldn't increase. So you can easily understand the physical reasoning behind it. It can also be proved mathematically, and of course you must, we should introduce some assumptions. It's quite a long demonstration, so let's forget about it, because it's not really important. What is important for us to remember is that in the rational formula, you should plug in a rainfall intensity for a rainfall event whose duration is equal to the time of concentration of the catchment. Okay? A question could be, yesterday I said the time of concentration cannot be measured, so your question could be, how can I estimate the time of concentration? There are some empirical formulas. I'm not presenting these formulas because they are just empirical. But if you look on the literature, I could put a link. If I remember, I put a link in my notes here. I put a link here. There are, if you look on Google for time of concentration, empirical formula, you get a lot of formulas. In Italy, we use a formula that is called the formula di Giandotti, and it's not used abroad. Typically, these formulas they are empirical, so they are estimated on the typical climate of the country where they were proposed. It's important to note that there is a lot of uncertainty in the definition of the time of concentration. Even if you use the empirical formulas, you must take into account that it's, there is a lot of uncertainty. Okay, now the second question is, given that I got an idea of the duration of the rainfall event, how can I estimate rainfall intensity? This is another topic that we don't deal with here, because usually this is dealt with in basic hydrology courses. It takes some time to discuss this topic, which is estimation of design rainfall. We are focusing on estimation of design flow. And you see that it's already a complicated matter. The estimation of design rainfall is complicated as well. But on the other hand, from a professional point of view, from a technical point of view, there is just one very simple equation, a relationship that gives to you the design rainfall. Of course, in this equation you understand that this equation must be flexible, because design rainfall depends on the location. And therefore, this relationship that now I'm writing, of course, must contain parameters, because it needs to be flexible. So the relationship is, as I said, very simple. If we call the rainfall intensity, which depends on the duration of the event, but also depends on the return period, of course, you understand it must depend on the return period, because we are talking about an extreme value, like for the design flow. This can be expressed through a parameter A, which can be proved typically depends on the return period times the duration of the event to the power of n, where n is another parameter which doesn't depend much on the return period. It typically depends on the location. Here I didn't include the location as a specific independent variable, because I'm implicitly assuming that I'm referring to a location, to a given location. So this is the formula. You see that it's very simple. The problem is, of course, to estimate these parameters. And this is a bit, as I said, long to discuss. What is important for you to know is that typically in the literature you find indications for these parameters depending on the location. And so basically, if you refer to Bologna, for instance, and a record period of 100 years, you should find in the literature that A, for a record period of 100 years, is about 50 millimeters. And, sorry, I forgot one thing. It's n minus 1. And n is about 0.6. And if you, the fact that n is about 0.6 means that if you look at the graph of this equation, d as a function of d, you get a graph like this one. Decreasing intensity for increasing duration. Because d is negative. D is elevated to a negative power. N is always lower than 1. As I said, if you look in the literature, there are indications for these parameters. And therefore, once that you know D, you can get the estimate to plug into the rational formula. There is uncertainty in the definition of the design rainfall, but we could say that the uncertainty is relatively limited. Because usually design rainfall is estimated on the basis of a lot of data, because as I said, rainfall observations are widespread. And overall, it's a phenomenon that is very easy also to measure, while the peak flows are very complicated to measure. Because this, we didn't discuss about this issue, but the river flow cannot be measured actually. It can be, we can measure the water level, and then there is a conversion curve between water level and river flow, which is called the rating curve to be used. And therefore, even in the measurement of the river flow, there is uncertainty. And also there is to say that in the measurement of the peak flow is complicated because usually during a flood, we don't have the means to measure because typically people don't get close to the river to look at the water level. And also this conversion curve, rating curve, which I mentioned, is not very reliable for high flows. So, as I said, estimation of the rainfall intensity is affected by uncertainty like any hydrological estimation, but we could say that the uncertainty is relatively limited. Okay, so one question that you may ask me is what is the location of rainfall? Because if the watershed is very large, if the catchment is very large, like the Po River, what location should I consider for estimating the rainfall? And this would be a good question. And what is done in the operational practice is to estimate rainfall in a central location in the watershed. So you look where you have the opportunity to get the parameters of this relationship. And then you make an attempt to refer to a central location in the watershed. But then, given that this gives an estimate of point rainfall, while you should consider for large catchment an area rainfall, because rainfall is spatially varying, you have to correct this estimation to take into account this spatial variability. And there are empirical formulas which are called areal reduction factors, which we are not discussing, because as I said, we are not discussing here estimation of design rainfall. But it's easy for you to, if you didn't get this preliminary background, it's easy for you to get it from the web. And you just must know the terms to search for. So now I delete the blackboard and I write down the terms that I mentioned to you, okay? So about this relationship that now I deleted, which allows you to estimate the rainfall intensity, it is called depth, duration, frequency, curve for rainfall. So this is the key term to search if you want to learn more. It is not required. I will not ask you at the exam to speak about rainfall estimation unless you do so. If you do so, if you speak about rainfall estimation, I listen to you. But I'm not asking questions on that. And please beware that you have to be aware of the difference between rainfall depth and rainfall intensity. The intensity is given by the rainfall depth divided by the time. Okay, you must be aware of the difference because these curves can be expressed in different forms depending on whether they give to you an estimate of the depth or the intensity. But given that you know the duration of the event, it is equivalent for you, but you must be aware of the difference. Okay? And then the second key term to search for is area reduction factor for rainfall. I am probably going to include these suggestions here. Now they are not there. Even the mention to aerial rainfall, if not, I realized that I didn't include it. So I'm probably going to update this page in order to include these references. Okay. So this is how to estimate I here. And then C. C is a runoff coefficient. In principle, C should be constrained within the range of 0, 1. For obvious reasons. It's 0. 0 means that it rains and you don't see any flow in the river. It may happen if the catchment is very dry and the rainfall is not really heavy, so it may happen. And 1 is equivalent to say that all the rainfall is finally converted into river flow without any losses. It may happen if the catchment is very wet, it's very humid. And then you get rainfall and you see all the corresponding water volume flowing into the river. It may happen, typically it happens also in impervious catchment. Like over a roof, you see that everything is converted to flow. Everything of rainfall is converted to flow. It may also happen in some cases that you experience runoff coefficient greater than 1. It may happen during a snow melt, so you don't see any rainfall, but you see a flood. These are typically floods induced by snow melt. They are very well discussed in the literature. Snow melt floods. It may also happen if you have some karstic flows. So basically, if you have some flows, underground flows, along preferential pathways, like in karstic areas, I hope you understand and my pronunciation is correct. Karstic means that you have big holes in the underground, and then it may happen that there is some rain that rained very far, so out of the catchment, that produces river flow because the water follows these big holes underground. So in karstic areas, it is common experience to see values of the runoff coefficient greater than 1. But usually we assume that it's lower than 1 because this happens for the great majority of the catchment and the events. Another issue that you should consider is that the runoff coefficient is not a constant. It depends on the considered event because it depends on the previous soil moisture, and also it depends on the type of meteorological forcing. Because typically during floods you have higher values of the runoff coefficients, and when you have instead events that are not so intense, you get lower values of the runoff coefficient. And this is understandable because during a flood usually you have a saturation of the watershed, and therefore the runoff coefficient increases because the watershed gets very humid, very wet. And so basically what we do is to define a runoff coefficient value that applies for floods because we want to use it in the rational formula. And there is a rule of thumb which says that it is generally varying for typical Italian catchments, which are, they are quite impervious. It typically varies between 0.4 and 0.7. So this is the estimate that basically we can take. And you may say, well, this is very good because there is reduced uncertainty. I mean, from 0.4 to 0.7, you may say it's not a big difference. Indeed, it is a big difference because if you think in percentage terms, passing from 0.7 down to 0.4 means that you have a reduction of 50%, more or less. So 50% means that your estimate for the design flow is affected by an uncertainty of 50%, which is not negligible. So basically, it looks like there is not much uncertainty in the definition of the runoff coefficient, but indeed there is. So basically, what is my suggestion? My suggestion is that this formula is employed not to get a precise estimate of the peak flow, but it's very useful to get an idea, a first idea of the order of magnitude. It is extremely useful because, as I said, the catchment area, usually you know it. And even if you don't know it, it's very easy to estimate. You get a topographic map and you estimate it. And the rainfall intensity is also easy to get because any professional that is used to work like an engineer that is working in Italy knows what is the typical rainfall intensity for a record period of 1 year in different regions in Italy. So it's very easy to get this estimate. The runoff coefficient is, let me say, easy to guess because if you want to stay on the safe side, you could get 1. And therefore, this formula allows you to make a very rapid computation, almost online. You get over a catchment. If you know the area, you have an idea of the rainfall intensity, you use a runoff coefficient of 1, and you get an upper estimate for the design flow. And this is very useful in order to get an order of magnitude. So, the rational formula must be interpreted in this way. It's very useful to provide you with an order of magnitude. And then you may say, okay, the runoff coefficient may be varying between 0.4 and 1. You get the range. And you already know, after 5 minutes, what is the range that you may expect from your catchment. And then you look at the catchment. If you see that there is a lot of impervious areas, you may think, okay, it's probably closer to 1, close to 1. If you see that the catchment is indeed very permeable, because you see a lot of, for instance, a lot of soil, not rocks, soil, and then you can say, you can easily correct your estimate. So it's indeed very useful. And the experience shows that this first guess is not so far from what really happens. And especially if you consider that as an engineer, you must always stay on the safe side. Okay. There are some assumptions embedded in the rational formula, which are implicit in its use, and it's important to try to put them in evidence. And for instance, I make to you an example of an assumption which I implicitly took. I said that the estimation of the retro period of rainfall should be, let me say again, I said that rainfall should be estimated for a given retro period. And you can understand that probably the retro period should be the retro period that is assigned for the peak flow. So you may understand that probably if I need to estimate the peak flow for a retro period of 100 years, probably the rainfall intensity that I should plug in there should be corresponding to a retro period of 100 years. But this is an implicit assumption. We are assuming that, implicitly, that the retro period of rainfall is the same of the retro period of the corresponding flood, which is not true in practice. It's not true. Why it's not true? Because I already told you that the same rainfall can induce different river flows depending on the humidity condition of the catchment. So it's not true that they have the same retro period, because I may have a rainfall with a retro period of 100 years and no flow in the river because the catchment is dry. So this is an assumption, an implicit assumption, which can be tolerated because this is an empirical formula to get an order of magnitude. But let's discuss all the assumptions, and